Welcome to the Chemistry 209 Masterclass series. This series of lectures is intended to highlight the key concepts of introductory spectroscopy and structure. This lecture, Masterclass 12, summarizes photoelectron spectroscopy. In Masterclasses 2 and 3, we saw that atoms have an infinite number of quantum states that converge to the limit where the principal quantum number is equal to infinity. The same is true for molecules. This convergence limit is a precisely defined energy above which the electronic wave function is no longer confined to the Coulomb potential associated with the positively charged nuclei. In other words, the upper limit of electronic excitation energies is the ionization limit, which corresponds with removal of the electron from the atom or molecule of interest. If we surpass this limit via excitation with light, the resulting photoionization process causes ejection of an electron from our atom or molecule. Photoionization is essentially the atomic and molecular analog to the photoelectric effect. We find that when the ionization energy of our atom or molecule is exceeded by photoexcitation, the resulting photoelectron kinetic energy is linearly dependent on the light's frequency. The principal difference between photoionization of atoms and molecules and the photoelectric effect is that, unlike bulk materials, atoms and molecules have discrete quantized energy level structure. This has important bearing on the observed photoelectron kinetic energy distributions. Conservation of energy and momentum dictates that when a photoelectron is ejected from our atom or molecule, the nascent ion must recoil in the opposite direction. Owing to the huge mass imbalance between the ion and photoelectron, we can make the assumption that the ion's kinetic energy is negligible, thereby simplifying our treatment of the photoionization process. As a result, we can view the photoelectron kinetic energy as being the difference between the photoexcitation energy and the sum of the ionization energy and ion internal energy. For example, consider photoionization of atomic neon. If we excite neon with a high-energy photon such that we remove a valence 2p electron, we produce neon plus in its electronic ground state. The sum of the electron kinetic energy and ionization energy must equal the photon energy. If the same photon instead removes a 2s electron, neon plus is produced in its first excited electronic state. Since it takes more energy to reach the first excited electronic state of the ion, the correlated electron kinetic energy is lower. We could also view this in terms of the greater amount of energy required to remove the 2s electron compared to a valence 2p electron. Removal of a 1s electron is a very high energy process. As a result, corresponding photoelectrons have a comparatively low electron kinetic energy. Using our knowledge of atomic term symbols, we can assign the peaks in the observed electron kinetic energy distribution to electronic states of the ion. The highest electron kinetic energy corresponds to the lowest electron binding energy, and the lowest EKE corresponds with the highest electron binding energy. The same logic can be applied to molecular orbitals. However, in this case we must also consider the vibrational energy level structure of the neutral molecule and ion. In principle, we should also consider rotational energy level structure, but we'll not worry about this in Chemistry 209. In the example shown here, we are considering photoionization of molecular hydrogen. Since we are removing a bonding electron, we expect that the bonding character of the molecular ion should be considerably different from that of the neutral molecule. This expectation is confirmed by the potential energy diagrams for H2 and its molecular cation, where we see that the ground electronic state potential energy curve for H2+ is more shallow and shifted to longer bond length relative to the neutral ground electronic state. As a result, the neutral ground state vibrational wave function has appreciable Franck-Condon overlap with a number of vibrational wave functions of the molecular ion. Thus we expect a distribution of photoelectron kinetic energies that is determined by the vibrational wave function overlap integral. Now we will define two different ionization energies, the adiabatic ionization energy and the vertical ionization energy. The adiabatic ionization energy is defined as the energy difference between the V equals 0 levels of the neutral molecule and the ion. The vertical ionization energy is the most probable ionization threshold accessed from the ground vibronic state, as defined by Franck-Condon overlap. In the case of molecular hydrogen, we find that vertical ionization occurs to the V equals 2 level of the molecular ion. We also see that a long progression of peaks is observed in the photoelectron spectrum owing to the relative offset of the H2+ potential energy curve compared with that of the neutral molecule. We can conclude that a long vibrational progression in the photoelectron spectrum is indicative of a significant change in bonding character upon photoionization. We can describe three general scenarios for photoionization and the resulting photoelectron spectra. The first is loss of a bonding electron. In this case, we expect a decrease in bond order, a reduction in vibrational level spacing, and an increase in bond length for the ion compared to the neutral. Consequently, a long vibrational progression is often observed in the photoelectron spectrum. The largest changes in bonding character are associated with removal of the most important bonding electrons, those that are low in energy and are especially stabilizing with respect to the molecular nuclear configuration. So we can expect that removal of the most important bonding electrons will result in the longest progressions in photoelectron spectra. Loss of a non-bonding electron, on the other hand, has very little impact on the overall bonding character. We find that the bond length and dissociation energy of the ion are relatively unchanged compared to the neutral if a non-bonding electron is removed. As a result, only a relatively short vibrational progression is observed in the photoelectron spectrum. The third scenario is removal of an antibonding electron. In this case, the bond order increases, as does vibrational spacing and dissociation energy for the ion compared with the neutral. We see a reduction of bond length owing to the enhanced stability of the molecular ion. As a result, a relatively long vibrational progression is observed in the photoelectron spectrum. Again, the largest changes in bonding character are associated with removal of the most important antibonding electrons, those that are high in energy and especially destabilizing to the molecular nuclear configuration. Of course, these three scenarios only provide rough guidelines for interpretation of photoelectron spectra. There are a number of factors that can give rise to seemingly anomalous behavior. Photoionization of valence electrons typically requires ultraviolet excitation. To remove core electrons, we require much higher energies and must instead photoionize with X-rays. Since chemical bonding is a valence electron phenomenon, binding energies of core electrons are predominantly defined by the nature of the atom. For example, the 1s binding energies for carbon atoms are approximately the same in all molecules. Differences between binding energies for atoms and molecules compared to that of the free unbound atom arise due to the chemical environments of the bound atoms. For example, the 1s binding energy of free atomic carbon is about 285 electron volts, whereas the 1s binding energy of the carbonyl carbon in acetone is approximately 292 electron volts. This chemical shift can be attributed to the fact that the carbonyl carbon is bound to an electronegative oxygen atom. The oxygen atom draws electron density away from the carbonyl carbon, thereby increasing the effective nuclear charge experienced by the 1s electron. Note that for X-ray photoelectron spectroscopy, broad spectral features without vibrational structure are observed. This is a result of the relative instability of core electron holes and the uncertainty relation between energy and time. Core hole decay typically occurs by relaxation of a valence electron to fill the vacancy in the core atomic orbital. This relaxation is accompanied by emission of an X-ray photon that is characteristic of the atomic energy level structure. In some cases, core hole decay produces secondary photoelectrons through the process of Auger emission. Kinetic energies of Auger electrons are also unique to each element and are also regularly used to characterize chemical samples. X-ray photoelectron spectroscopy is the highest energy process that we will explore in Chemistry 209. For Master Classes 13 and 14, we will turn our attention back to the lowest energy region of the electromagnetic spectrum and discuss nuclear magnetic resonance spectroscopy. See you next time.